All right.
So
I will mostly be up front, but the pictures will supplement because I can't draw that.
yeah, draw fractal and finite time.
No, I mean, the computer can't either, but it's a better job.
Right, we're delighted to have Becca Winarski here from the College of Holy Cross. Becca and I met several years ago at the University of Michigan Athletics Department, where she was a postdoc. Were you there too?
No.
Or at some point, yes. Okay.
I mean, I was there one time, but not as a postdoc. Probably wasn't there when you were there.
Yeah, so she works in complex dynamics, which has the best pictures, so we had to bring her. And also, as I mentioned in the email, we went to this conference on communicating mathematics. Most math talks are impossible to understand and a waste of time for everyone involved. And the idea is to make math talks where everyone understands everything. So this is our job, 6 of us, to make sure that we understand everything that she says. So ask questions, ask for examples. Let's do it.
Yeah, so thanks, Diana. I'm excited for the format, but I'm also a little bit nervous because I've never given a talk like this. So I think you are more experienced at being an audience for these talks than I am at giving a talk in this way. So it's a learning experience for all of us. I'm looking forward to it. And thanks for inviting me to be part of this sequence. This seminar. Okay, so I will be talking about all sorts of fun things today, but centered around talking about polynomials.
Yeah, that's a good idea.
Yeah. Oh. Dynamics and trees. And so I'll be talking about some of my recent-ish research that is joint with Jim Belk, Justin Lanier, and Dan Margalit. Right, let's spell his names. Okay, and so the goal is to like classify. That's not how you spell goal. That's how you spell classify. Goal is to classify / understand the dynamics of polynomials. And we'll talk about different versions of what that means. And when we talk about polynomials, it's really tempting to just think about them as a formula, but we really want to think about polynomials as functions, as doing something to, we'll think of them as functions of complex numbers. And in particular, what we'll be interested in is if we have some polynomial, call it P, we're going to apply it over and over. So we can apply it as many times as we want. We want to look at what it does to the critical points. Critical points meaning from calculus, the derivatives, or places where the derivative is 0. So we take the critical points and we apply the polynomial over and over to them. And we want to study the long-term behavior of those critical points. By the way, when I say p to the n like this, I mean composition. So p squared of some complex number means p of that complex number. Okay. So let's focus on quadratic polynomials. Everything I say today works for higher degree polynomials, but it's easiest to state when we talk about quadratic polynomials. So we're talking about quadratic polynomials. Remember, these are functions in terms of speed. So their coefficients can be, C, polynomials. I'm just using slides. I'm very bad at spelling on the board. and I've been on sabbatical, so I'm out of practice. Quadratic polynomials. So these are, I'm going to use the variable as z, where z can take in complex numbers, and it has coefficients that are also complex numbers. So our quadratic polynomials are a z squared plus bz plus, I'm going to say d, I'm going to skip the use of c for now. And so these are all complex numbers. And z is a complex variable. But we can use a change of coordinates, like in multivariable calculus, to take a quadratic polynomial of this form to a quadratic polynomial of the form z squared plus c. And the change of coordinates that we would use to do this is z over square root of a minus b over 2a. So if we just replace these z's with z over square root of a minus b over a, we can get something of the form z squared plus a constant. And the benefit of doing this is we are interested in studying the long-term behavior of critical points. Here, no matter what c is, my critical point is always 0.
I have a question.
Yes.
So you're saying if you substitute z over the square root of a minus b over a for z in the previous expression, it turns
Yes.
into z squared plus c, where c is only in terms of a and b. MDD.
Yes, that's right.
Okay.
And yes, exactly. And by the way, maybe the better way I could have done this would have been to use a different variable here, so that I was using like the variable w over here and the variable z over here, and then I would have like v equals w. No, that's the wrong way. W equals z over that. That's what I mean. Yeah, and so we're doing this because we're just sort of thinking of shifting the plane around when we do this change of coordinates, so that we can write roughly equivalent polynomials, dynamically equivalent polynomials, where their critical points are always 0, because they're easier to understand. And in fact, one reason we might do this is because we now can study what happens as I vary c as a complex number. So z squared plus c is my polynomial. What happens to the critical point and all of the points that I get when I repeatedly apply the polynomial to it. So that's looking at the set p to the n of 0 as I vary c. And one way of answering this, or one behavior that we're interested in, is, for example, for what c is the set p to the n of 0 bounded? or we could even say finite, as n goes to infinity. So a priori, this could be an infinite set, right? We repeatedly apply a polynomial to 0 infinitely many times. We could get infinitely many points. They could go to infinity. They could do all sorts of crazy things. But what we're interested, or one way of studying the dynamics of polynomials as a whole is to ask which polynomials have sort of nice behavior. Which polynomials have this behavior that the complex number, or sorry, the critical point gives us a finite set when we repeatedly apply our polynomial to it and study the dynamics there.
Can you give an example? Are you going to give an example, like a simple
I
example?
will give a simple example.
Okay.
But before giving a simple example, I wanted to give all of the examples.
Okay.
So here I'll direct your attention to my slide. So here I've shown the Mandelbrot set. So what is the Mandelbrot set? The Mandelbrot set is a set of numbers, complex numbers, it's the black part, with the behavior that my set, p to the n of 0, is bounded. So now I will give an example that's in the Mandelbrot set. So z squared, this is where c is equal to 0. The critical point is 0. It maps to itself. So if you plug 0 into z squared, you get 0. If you plug 0 in to z squared and then z squared again, you get 0 and then 0 again. And so anytime you apply z squared to the point 0, you just keep getting 0 back. Therefore, this set p to the n of 0 is only 1 point. It's only 0. And so 0 is in fact in the Mandelbrot set. It's right here. Similarly, -1 is in the Mandelbrot set. And why is that? Well, when c is -1, my critical point is 0. I plug 0 in to z squared minus 1. I get -1. So then if I want to know what happens when I apply z squared minus 1 again, I could think of plugging -1 into z squared minus 1. That's what happens when I put 0 in to z squared minus 1 twice. And -1 goes to 0. Therefore, I get back to where I started. If I repeatedly apply z squared minus 1, I'm just going to get to the point 0. I'm just going to flip between 0 and -1. So again, I have a finite set. It's in fact bounded. And so -1 is also in the Mandelbrot set. Okay. I have an exercise for you now. So here I've shown an example where the critical point is 1 periodic, right? 0 maps to itself, where the critical point is 2 periodic, 1 maps to -1, -1 maps back to 2. So under 2 applications, I get back to 0. What about 3 periodic critical points? I have 2 questions, and these are for you to work on. So we're looking for 3 periodic critical points. So remember, 0 is the critical point. With what or which values of c, which values of c give us a 3 periodic critical point, meaning 0 is 3 periodic. Okay, so there's two parts to this exercise. Part one is how do we do it? How do we find values of C that give us this three periodic behavior? And question two is how many values of C give us this three periodic behavior? Okay, so this is your exercise. I'll give you a few minutes to work on this.
What's Jane, I agree. We take that part of the board that we're, what part of the board is,
Oh, yeah.
Yeah, sure.
Why
We'll
don't
get
you
further.
use the boards in back?
Yeah, that's a good idea.
Thank you.
And there's one on the side too.
So, we know that, when we plug in 0 the first time into this polynomial, it gives us C. So, the first iteration of be C. And then when we plug C again into it, we get C squared plus C. And then when we plug this, into the function again, we get C squared plus C all squared plus C. But since we only want to have 3 different points, we know that this one has to be 0 because we know that the next point is going to be C. So the only point we can plug into this function to get C is 0. First one is C. So we know that C squared plus C all squared plus C is 0. And then we just expanded it and canceled it out. Well, we got a function of like C times C. Well, there's like C equals 0 is going to be this part. So we actually also count the one that was like here in this. So it should be like it's actually a cubic that gives us the other solutions that are non-zero. And so that let us think that well, the cubic has 3 solutions. And so there should be 3 different points that.
Perfect. Yep, that's better than I could have explained it. Thank you. Yes, exactly. There are 3 solutions. And I heard mention of rational root theorem, which is great if I had asked you what they were, but I didn't. And the reason I didn't is because none of them are rational and 2 of them are complex. So just as a summary to the answer here, there are 3 solutions. One is real, and the other 2 are complex conjugates. And so these are 3 different values of C that then correspond to 3 different polynomials. And these sometimes in complex dynamics give them names. The one that's real is called the airplane. And the other 2 that are complex conjugates are called the rabbit and the co-rabbit, where co-rabbit is short for complex conjugate of the rabbit.
So before you show them to us, I am like, based on Daria's picture, you should start at 0, then you should go to the first one, then you should go to the second one, then you should come back to 0. So I'm confused about how there are three new ones. I would think there would be 2 new ones other than 0. Like it starts at 0, it goes one place, it goes to the second place, comes back.
So there's 2 distinct questions here. The 2 distinct questions are how many points are there?
Yeah.
Versus how many values of C give us this behavior.
Oh.
And so they're separate because the value, so like when I ask what values of C there are, that means of all the polynomials that exist that are of the form Z squared plus C, how many of them have the behavior that 0 is 3 periodic?
Right, okay.
And then the values that correspond to C then give us these special points of C and C squared plus C, as Daria pointed out.
Okay, right, okay, because the second iterate isn't necessarily a value of C. It's not probably.
the second iterate is not a value of C.
Got it, okay,
That's correct.
okay, got it, all right, thank you.
Yes.
Gotcha.
Yeah, great. And I mean, this way of thinking about it, of 0 going to C and C going to C squared plus C, this is great because that sort of gives us a sense of like how we're moving in the complex plane. And by the way, I've mentioned the names of the polynomials, and the reason they're named the way they are is because of what your Julia sets look like. So what is a Julia set? So earlier I showed you the Mandelbrot set, which captures all of the values of C where the polynomial has a certain behavior. And this is sort of relating to Diana's last question. Whereas the Julia set is specific to a polynomial. And so the Julia set captures for that polynomial the complex numbers that stay bounded when we repeatedly apply the polynomial. So it's like an analogous concept, but in a different context. So here, the Julia sets correspond to each polynomial. And what's going on? Well, we know that 0 maps to C, C maps to C squared plus C, C squared plus C maps back to 0. So it's definitely true that 0, C, and C squared. Oh, sorry, I defined the Julia set just a moment ago. That definition was actually for the Phil Julia set. The Julia set is the boundary of the Phil Julia set, and so we can imagine. I didn't fill these in because it gets too cluttered, but the Phil Julia set like is this stuff with all of the blobs filled in. And so it's definitely true that there are points in the Phil Julia set because 0, C, whatever C is, and C squared plus C are always going to be in the Phil Julia set. But it turns out there's many other points, infinitely many other points, that when we apply Z squared plus C for one of our special values of C, either the airplane value, the rabbit value, or the kohlrabi value, respectively, we'll end up getting many points that stay bounded when we repeatedly apply the polynomial.
Could we just go back to Mandelbrot again? What is the difference? What is the
Yeah.
definition of Mandelbrot as opposed to?
Yeah, this is I was definitely confused about this when I first started learning it.
And every time I learn it, like, I'm like, oh, now I understand the difference between the Mandelbrot set and the Julia set, and then it
Yeah.
goes away, and then I have to
Yeah.
learn it again.
I was thinking that's with the definition you gave for the Julia set. Well, it's all, that is the definition of Mandelbrot.
So the definitions are actually the same. What matters is the domain.
Okay.
So the Mandelbrot set is
You
the
wanna write it down?
values of C where Z squared plus
So you're only
C stays
using
bounded.
Numbers.
Yeah,
When you plug in 0,
when you plug in
you
0.
wanna write it down, like, over there or something? No,
But C
okay.
is,
It's
C is
right-
a
written right
complex
there.
Right
number,
there.
right? Isn't C a complex number or is this?
Yes, it's a complex number. So we're thinking about this as the plane with like the real axis here and the imaginary axis. here.
Right, but C could be any number on that plane.
Yes. And the black set. Oh, okay, and the Julia set is specific to a polynomial. So, or the Phil Julia set. So if I've already chosen,
Just looking at one point.
The Mandelbrot set is like, I only care about 0, I only care about 0, what happens to 0, and the Julia set is like, you probably plug in, the Mandelbrot set only plugs in 0 to every polynomial. The Julia set plugs in everything to only one polynomial. But I think we should write, but I do think we should write that. I know it's written, but like, it's with more words.
It may or may not be helpful if you think. Well, restrict yourself to real numbers, right? Let's say you just pick, let me see. Now you can draw like a two-dimensional picture where you choose your polynomial by choosing C. And then above each value of C, you have a copy of the real axis, like this vertical axis. And you can look
Or
at,
the imaginary axis,
well,
the vertical axis.
you have like real cross real. So you just have like an X and, let's call them a C and Z axis.
Okay.
So if you, as you move along the C-axis, you're like choosing your polynomial. And then on every Z-axis, the vertical axis, you can apply the polynomial nomenclature and ask which points fly away. And then you can fill in, you know, in that two-dimensional picture, you can fill in the points that don't fly away, that stay bounded. And then the understanding of the Mandelbrot set is all of the points on the C-axis, where the shape you just drawn contains the zero on the Z-axis. I don't know what the thing would look like, but I would probably like a disk or something. But
Yeah, it could be like 4-ish dimensional. maybe?
oh, because if you say trivial stuff, then it's
Yeah.
like the
Yes, I think that's very visualizing.
the C-axis. Here's the Z. That's and like it's gonna be never Z equals 0. Here you have the polynomial Z squared. So 0 goes to 0, and then everything else flies away, right? Because if you have like a number greater than 0, then squaring it makes it bigger. And if you have a number less than 0, squaring it makes it negative, it's still bigger.
Unless
This
it's
is
less
like-
than 1? What about if it's less than 1 in magnitude?
So 1. If it's between 1 and -1, then it stays valid.
Yeah.
If it's not, then it flies away. So this is all of the stuff that stays bounded when C equals 0. Then when C equals, let's say, 2 or something. What happens then?
I think everything by the way.
Want to do it.
Yeah, okay. Because if you're close to 0, you can see you get about 1, you fly away. I mean, if you're at -1, you square it. Yeah, okay.
Yeah, so 2 is like here,
Yeah.
my picture. And if 0 doesn't stay bounded, nothing will.
Yeah. So, okay, I don't know if we can actually draw that sort of these vertical lines for any other band. It's gonna be hard, but the idea is, you're gonna have these vertical lines somehow for like every other location. And like sometimes that, the bounded band goes to 0. And sometimes it doesn't. And like ones that go to 0 are part of the
Oh.
process.
Oh.
And the Mandelbrot process is just a set on the C-axis. I don't know.
I really like that way of thinking about it.
Okay.
Yeah, thanks for elucidating my ways of thinking about this. Another way that I like to think about the Mandelbrot set versus Julia set is like, if I look at the Mandelbrot set, I can pick any point in it. And then that point has a corresponding Julia set. And so this is sort of building on what Diana said, that the Mandelbrot says, I look at what the Mandelbrot says, I look at 0 under everything. And then if I pick one thing in there, I can like look at everything with that specific C squared plus C.
Okay.
These are really light. Can you see them?
I can see them.
Okay, great.
I'm turn on one light.
You want to turn off more?
I
One
think
is
these
on.
are my last fractal pictures. From now on, I'll draw cartoons. By the way, maybe if you're really creative, you can see why these polynomials are named the way they are. Like this, it looks like an airplane from the front. If you're really creative, this looks like a rabbit, and then this is the complex conjugate of the rabbit.
Okay.
Yeah, great. By the way, for fun, I'd like to include one more example of a value of C that's in the Mandelbrot set that's unrelated to this airplane rabbit. And that value is I, because I is a little bit different than the examples that we've seen before. C equals I means that I have the polynomial Z squared plus I. Unfortunately, I don't have a Julia set for it. But let's look at the critical point and what happens to it. So the critical point is 0. If I plug 0 in, I get I. If I plug I in, I get I squared plus I, so -1 plus I. If I plug -1 plus I in, I get -1 plus I plus I.
Squared.
Thank you. That's why there's parentheses. And I did the calculation before, so I'm gonna cheat. This is 1 minus 2I minus 1 plus I. And that's minus I. And then if I plug minus I in, I get the same thing that I previously did when I plugged I in. Minus I and I should do the same thing here. And so what's going on? Well, 0 is mapping to I maps to -1 plus I maps back to -1 plus I. And so now if I keep applying the polynomial, I'm just going to swap between -1 plus I and minus I. And so this set is bounded, but my critical point is not periodic. It's what we sometimes call pre-periodic because it eventually becomes periodic. By the way, I want to give this set a name. So the set that I'm referring to is what I get after applying the polynomial to 0, any number of non-negative, any positive number of times. So I'm going to define the post-critical set as, I'll call it P. No, I won't, because my polynomial is called P. I will call it M for the polynomial P. And this is going to be the set of points that I get from applying my polynomial any number of times to 0, but I don't necessarily want to include 0. So for example, in this, I'm going to look at everything that 0 eventually maps to, but it does not eventually map to itself. So I don't want to include 0 in here. I just want to look at, this is P of 0. This is P squared of 0. This is P cubed of 0. And then also P to the 4th, P to the 5th, etc. So my post-critical set will be everything that comes after 0. In the case of z squared and z squared minus 1, 0 is in its own post-critical set, and the rabbit, co-rabbit, and airplane. 0 is in its own post-critical set, but it doesn't have to be, is the point. Okay. Great. So this is our primer on polynomials and the dynamics of polynomials. But what we actually want to look at are maps that are kind of like polynomials, but not quite. And so we want to abstract the notion of polynomials. And here's the way we're going to do that. I guess I could have kept the word polynomials, since that's what we're going to talk about next. We've always been thinking about polynomials as maps from C to C. So we're going to think about C as a plane. And the behavior that we want to capture of polynomials is that they are continuous. So what we mean by this is if I take some point in my codomain version of C, and I take some little open disk around it, the pre-image under the polynomial here is a bunch of the pre-images of this point with little open disks around them. So that's what it means to be continuous. Okay. Polynomials are continuous. We know this from calculus, but the notion generalizes to other types of maps, which we also know from calculus. Another property of polynomials that we want is that they are usually d to 1. So what does that mean? There's a lot. There's actually two things to unpack here. I'm going to focus on the d to 1 part before I focus on the usually. So d to 1 just means that if I have something in my codomain, it has d things mapping to it, usually.
Like a parabola.
Like
has
a
two things.
parabola, yeah, great, thanks, Diana. For instance, a parabola has the property that if I look in my codomain, it usually has two things mapping to it. But it doesn't always have two things mapping to it, right? Right here, it only has one, or sorry, if I look at that point of my codomain, only one thing maps to it. So usually two things map to it, not always. So z squared is a really good example to keep in mind when I'm talking about things being 2 to 1, usually. Because 0 in the codomain has the property that only one thing mapped to it. I shouldn't have erased the parabola. That was incredibly useful. Thanks, Diana. Only one thing maps to it. 0 maps to 0. Nothing else maps to 0. But and then it's also true that if I look near 0, near 0, if I have some point here, actually let's go here, something on the real axis. It has two preimages near 0. Likewise, any other point in here is going to have, that was a poor choice, but it will have two preimages.
But what about negative points on the real line?
Negative points on the real line.
They don't have any preimages.
We're looking at complex numbers.
Oh, so they do.
So they do.
Oh, that's so good.
Yeah,
You're so right.
This is exactly why we look at complex dynamics and not real dynamics.
Right. Sorry, I forgot for a second. I forgot where I was.
And so we have, so if we take something with a negative, on the negative real line, its preimages would be on the imaginary axis.
Oh, okay.
Those are actually really easy to draw.
You still need the presentation?
I think I don't.
Okay.
Yeah,
I was gonna try to think about something. There will you.
Okay.
But
Great.
if you use it again, let me know and I'll.
Okay. Great, thank you. Thank you for
Yeah.
assisting me with that projection. I don't think I need anything else.
Great.
I guess I have backup. If you don't want me to draw cartoon rabbits in the future, I have extra slides.
Let me know when.
Okay.
it happens.
I was really planning to draw the cartoons, but great. Okay, so near 0, the map is still mapping 2 to 1. And it's sort of mapping 2 to 1, like kind of symmetrically, like this point has two preimages that are sort of rotated around 0. This point has two preimages, one's above 0, one's below 0. So near zero, this map is 2 to 1. At 0, it's 1 to 1. But the behavior sort of around 0 sort of looks like rotation, where there's like some symmetry by rotation around 0. And the way that we say this is near 0, it looks like z squared. I mean, here we were actually looking at z squared, but what usually means is there will be some points where you don't map d to 1. And at those points, you look like z squared or z cubed or something like this, where you're doing this sort of rotational behavior. Okay. I want to codify this into like, yes.
Is there any condition that the image that here you get different disjoint set?
Yes. We want the preimages to be disjoint, but as long as we choose a small enough open set here, we can make sure that that happens. So we just need the existence of one set so that they're disjoint. Yeah, thank you for clarifying that.
Can you just confirm, you said you want them to look like z squared near 0, not like
Well,
z squared number?
Z to the d.
Okay.
In this case, we were focusing on z squared. So I actually wanted to like give this a definition or give this a name, and then I'll write out the definition very specifically. And
Sorry, you
I'll
had
take your comments into consideration when writing this definition.
Daria, you had a comment.
Yeah, I was wondering, for d to 1, so usually d to 1, isn't it always, well, since it's a function, it's like always something to 1, so are you saying that d is like larger than, or what, I guess what is d?
Okay, so d to 1 is sort of capturing this usually, like the point here is that it captures this like usually, or sorry, d to 1 means that d is going to be the same for all but a few points.
Oh,
so
it's constant to 1.
Yeah,
Okay.
exactly. It's constant to 1 usually.
Yeah.
Yeah, thank you. Yeah, thank you. D is a constant. That's the answer we're going for. Okay. So I want to name a topological polynomial. This will be the definition. And it will incorporate all these properties of polynomials that we just discussed. Okay, so the properties that are important are that it's continuous, meaning for each point, I look at its preimages, I can find an open disk such that the preimage of that open disk is a bunch of disjoint disks, each one surrounding a preimage of Y. We want it to be d to 1, where d is a constant, at all but finitely many points. These finitely many points are what we'll call critical points. If we have an actual polynomial, these are the places where the derivative is 0. If we don't have an actual polynomial, these critical points are the places where the image of them is not d to 1 at some of the points, or said differently, at the critical points, the map looks like z to the k for some k less than or equal to d.
It doesn't have to be the same as D.
It doesn't have to be the same as d. So
Okay.
in the example that we saw, because 2 is pretty small, if you're not 1-to-1, or if you're not 2-to-1, you must be 1-to-1. And so near 0, we looked like z squared. However, if we're looking at quadratic polynomials, or places where, or maps where d is 2, k and d will be equal. They'll both be 2. But in the case where d is bigger than 2, so say d is 3, we could have critical points where the map looks like z squared.
Okay. Doesn't have to be a divisor or anything.
Doesn't have to be a divisor or anything.
Amazing.
Just has to be less.
Okay.
This actually matches some of our intuition about calculus, or not even from calculus, from algebra, where when we look at a polynomial, so I'm focusing now on things where I can write down formulas, but I don't have to. So if I have something like a polynomial, say z minus 1 squared, I'm gonna leave my, let's say that this is the derivative. Z plus 1. If my derivative is something like z squared minus 1, sorry, z minus 1 squared, z plus 1, I have 2 critical points. I have 1 and minus 1 as my critical points, but they have different behaviors. This is like a double critical point, and this is a single critical point. And being a double critical point means that being a single critical point means that near that point you're going to look like z squared. Being a double critical point means that near that point you're going to look like z cubed. And so it's possible to have critical points of different orders. We've seen that in calculus. And that's exactly this behavior that we're capturing, where you look like z to the k, where k just needs to be less than your total d. By the way, d is the degree of a polynomial when we're looking at actual polynomials. We can use that term to refer to these topological polynomials as well. So I'm going to include that vocabulary so that I don't have to keep saying d, the d that we have or whatever. So this is called the degree. Just like it's called the degree for polynomials. So, yes, so basically, what a topological polynomial is it's something that behaves like a polynomial, but you don't necessarily have a formula for it. And that's kind of the goal. By the way, here's the thing, I just saw it now. So the goal of this dynamical behavior is to determine which, if any, sorry, let me take a step back. A polynomial we can think of as a topological polynomial. Because they are, the definition of topological polynomial was designed to abstract the notion of a polynomial and to capture a certain set of relevant properties. So a natural inverse question is, when can I go the other way? When is there some sort of notion of a polynomial that captures something about this topological polynomial that is somehow similar to this topological polynomial. And in order to answer this question, I want to first codify what I mean by somehow similar to. The notion of equivalence of topological polynomials. So if I have two topological polynomials, I'm not calling them P anymore because they're not polynomials. They're these like abstract things.
Will you give an example of a topological polynomial sometime? Is it coming?
Oh,
Is it like a linear, would it be like y equals absolute value of x? Would that be a topological polynomial?
would it? I guess it would.
It's continuous, it's d to 1 and here's 0. I don't know.
Okay.
It's kind of like c squared, not a lot like c
It's
squared.
kind of like z squared. Is it a topological polynomial? Maybe. I guess under this definition it is.
Oh, I guess you could give it, can
Yeah.
you give another example of a topological polynomial?
Yeah. The way I think about topological polynomials does not involve me writing down formulas for them.
Or drawing pictures, or having a mental stretching. I remember like z squared,
Yeah.
takes a complex plane and stretches it like this.
Sure, yeah. So here's a really weird way to create a topological polynomial that is not a polynomial. We take a rabbit. Right, that's my rabbit. And the relevant part about the rabbit is that we have these three post-critical points. Remember, 0 maps to c, maps to t squared plus c, maps back to 0. It's our post-critical set. And in the complex numbers, my points are something like 0, c, c squared plus c. And so what I'm going to do is I'm going to like draw those points in. And I can take a curve surrounding two of them. The standard choice is those two. There's like, I'm not going to get to the actual twisting of rabbits, but I'm going to do what's called a Dane twist to this rabbit. And so what is a Dane twist? I take this curved gamma surrounding the two ears, I cut along the curve, I twist my plane by 2 pi, and glue it back together. It's hard to imagine. And the reason it's hard to imagine is because the outcome of a map like this still looks like the plane because it like the codomain is still the plane. But if I try to draw what it does to the rabbit.
Is it centered at one of those points? You're like, you cut along that, you get some disk that you take out.
Mhm.
And then do you sort of slice around it and twist it and put it back together? What are you doing?
I'm gonna attempt to draw this.
Yeah, that sounds good.
So I could imagine like, maybe I'll draw the curve a little smaller. So what I'm sort of doing is I'm like cutting the ears.
Off.
Sorry, rabbit. Yeah.
Glue it back together.
Yeah, cutting the ears off and then like pulling them around themselves and then gluing it back together. Yeah, it's really painful for the rabbits.
But in particular, the ear piercings stay in the same place.
You're what?
The
In
ear
particular,
piercings.
the ear piercings stay in the same place.
The ear
So
piercing.
if I just took that whole disc and just like flipped the entire disc around by 2 pi, I'm like, wait, nothing happened. I just rotated it by 2 pi.
That's right. The ear piercings need to stay where they are.
But you're twisting the ears, like when you draw these twisted ears, they
I
are
see.
quite twisted, huh?
So you take the rabbit, you put some little pins through its ear piercings to pin it to the table.
Yeah.
You then cut its ears off. You then stretch the ears around the pins.
Huh?
360 degrees, and then yeah, there we go. Okay.
And then you glue
Ouch.
the
Ow.
Yeah, it's really painful for the rabbits, I'm
roots.
sorry.
The roots of the ears get glued back on also, so the whole thing is still continuous.
Yes, exactly, exactly. And so doing this thing to the rabbit gives me a topological polynomial.
Hmm.
So the map that takes,
Of course, that was my second, that would be my second.
yeah, exactly. Well, like I said, I don't think of, I like to like separate topological polynomials from things that have formulas. And thus, I think it's actually a little bit misleading to think about topological polynomials as things that you can write down with the formula. And here's something that you can't. Actually, you can, but it's easier to not.
Yes, you have the ears after you twisted them, still attached to the body,
Yes.
but over there, you cut it off from the body.
Yeah, okay, so,
Or is that actually, you cut it, you hit it right where the top of the body was?
You'd have to sew it down along that, like ears down along that line, so that when you did a stretch. Like you'd nail down the piercings and you'd clamp along the cutting line to the rest of the ears. Before you stretch.
Is there any inverse transformation that can take the topology of the polynomial to?
that's the main point. I'll get there soon. But I need to, if I understand your question correctly,
Yeah, going from a topological polynomial to the polynomial.
yeah,
We can do this, but
yes.
if there is, what are the conditions of that transformation?
Yeah, I need to give you another definition, the definition of equivalent before I can answer that question.
Okay.
Sorry, why did that give a topological polynomial? The same.
Right, so what does it mean to be a topological polynomial? It means that you're continuous. It is still true that if I take any point here, I chose maybe selectively, let's go with this point because it's a little bit less believable. If I take this point here and I look at what mapped to it, I think it would be something like that. So I have open sets that have preimage, or open disks that have preimages that are open disks over here. And this map is 2 to 1, except at 0, just like the rabbit was. Doing this twisting thing didn't change that at all. And at the critical points, the map looks like z squared, because again, doing this twisting thing didn't change it at all. So basically, these two properties were unchanged under this twisting operation. The only thing that is kind of hard to believe is that it's continuous. But the fact that it's continuous follows from what's called the pasting lemma in topology, or the analogy that you've seen of this is in calculus, like in order for a piecewise defined function to be continuous, the two sides have to meet. It's sort of the same thing here, that because you twist in a way where you like pull everything around, and when you glue back, everything meets properly, it is actually continuous. So continuous is the hardest to believe. These two were unchanged by this map that didn't do anything to c and c squared plus c.
So the way you describe it, you take a point over there, it seems like you have to deal with the convex sets. If you don't have a convex set on that side, because if you take a small domain set around one of the points, if it's not convex, because the other side of your open set would be outside of the domain. So do you need a conditions dealing with the convex set?
For which part?
For topological polynomial.
Convex sets are unnecessary because topology allows you to just kind of move things until they are convex. This is where topological polynomials are like, they're very flexible. And so if a topological polynomial doesn't look convex, you can kind of just kind of mush it around until it is.
Oh,
We should stop soon.
Can I give the definition?
Okay.
And the
Yes.
main point?
Lunch closes though at 1:30, so we have to get in there, see?
Okay, so I will just give this definition of equivalence, yes,
Okay,
thank
yeah,
you for moving me along now. Yeah, giving the topological polynomial is very important, but also, took a while.
Yeah.
Okay, so I want to define equivalence, and then I want to give you the main point. So we say that two topological polynomials are equivalent. First of all, we want their post-critical sets. Let's say that we want them to be finite, just to make our life simpler. This is the post-critical set. Oh,
You said over there you
before.
called it MP, yeah.
Yeah, you do. For F,
Oh, yeah.
and then for G. We want them to be equal, and we also will assume that they're finite, just to make our lives easier.
The equal in size or equal in?
Equal in size, they have the same number of elements. And so I'm going to draw these post-critical sets. Or sorry, I'm going to draw these topological polynomials as maps. Instead of going from left to right, I'm going to draw them from top to bottom. So this will be F, and this will be G. And they are maps from C to C. But also, they are maps from C to C that need to map the post-critical set to the post-critical set. But this happens naturally, because what is a post-critical set? It's everything you get by applying the map to this to 0. And so applying the map one more time doesn't change that set. So I'm going to write that I want to take this set to this set. Similarly here. Okay, we say that these two topological polynomials are equivalent if we can create, if we can make a square where there are continuous maps, continuous bijective maps, H0, H1. Bijective. That are basically the same up to this mushing that I talked about earlier. Homotopy is the word for it, but if you've never heard of homotopy, it's mushing. But also that take the that also keep the proper sets where they are. Keeping MF where it is. So this is a very technical definition, but what I like to think of this as is just a change of coordinates of the complex plane. Like in multivariable calculus, you can do this you can take the complex plane in rectangular coordinates and shift it to in square coordinates and shift it to parallelogram coordinates. It's basically just doing that, except you can do wiggly coordinates. So you can do a wiggly change of coordinates is what this says. And the answer to this question, or maybe a better way of stating this question, when is a topological polynomial equivalent to a polynomial using this notion? And Thurston answered this question.
Oh.
Thurston says if F is a post-critically finite, meaning the post-critical set is finite, topological polynomial it is equivalent to a polynomial if and only if it does not have a curve or multi-curve. So a multi-curve just means, so I'll say union of curves that cyclically permute. With degree 1. Unfortunately, in order to get to the point, I think I failed the purpose of the seminar, which was for everybody to understand everything. Because the main theorem, the main point has a few words that I just ran out of time to tell you about, unfortunately. So in an effort to eat lunch, I think I have to end. But at lunch, I can explain what these things are. So I failed that purpose, but I wanted to get to this point that this dynamical behavior, like having the same dynamics as an actual polynomial, can only be prevented by the existence of like a curve or, you know, few curves. And that's kind of wild. Okay, thank you.
Yeah, all right, thank you.
Said with degree something. or
1.
With degree 1.